Today we've got Kevin Wright doing Audio 101 for everyone. It's going to be great. So just, sit back, get your notepad out, maybe some headphones, but Kevin will talk all about that here in a second. And so with that, let's go ahead and pass it on over to Kevin. Take it away, Kevin.
Sure thing. Yes. Thanks, Josh. My name is Kevin Wright. I'm an assistant technical director at NC State University Theater. And I've been doing that part-time and full-time for a combined almost 20 years now. Yeah. And so I'm going to go ahead and grab the screen and open up a presentation. And while you guys are kind of hopefully get a giggle out of this title slide, I'll give you a little bit more background about myself. I was always interested in music from early age. There was always music playing in the house, and then moving on to middle school, symphonic band, where I did well, and then eventually in the marching band in high school, and then I even had kind of like a rock and roll, garage band in high school that continued on to college. I entered the Poole College of Management at NC State in 1999. I wasn't really interested in business, but my mother insisted that I get a degree, so that one sounded kind of easy. And I won't confirm or deny that. But yeah, in the meantime, I actually started working part-time at Stewart Theater, and as a technician and a stagehand. And it pretty quickly kind of started to feel like home for me. There was very intelligent people, very creative people, and you got to climb around on catwalks and play with lots of cool toys. So yeah, I started to develop a real interest in that. And then by the time I finished my undergrad, I had sort of deliberately kind of set music on the back burner, and I really barely even pursued any work with my actual degree. I just kept freelancing in the area. I worked at other theaters. I worked for bands and clubs and stuff like that. And that's kind of how I kind of cut my teeth. But yeah, actually, no formal training or education, I should say, in audio. And what I've learned, I've taken from other people in the field, knowledgeable people, from the experiences I've had, and doing my own kind of my research on the side. So the scope of this presentation is going to be, we're going to start with the real basics and talk about sound waves and how sound interacts with the environment and with us. And then we'll kind of go over into how we capture that sound out of the environment, which is going to be microphones. So with that, let's just go right ahead. But yeah, all this stuff, yeah, we coil a lot of cable. You need to be able to coil cable to be a sound guy. Okay, yeah, so what is sound, right? So basically, you have an object that's in the environment that's vibrating, and it's imparting that energy into the air around us, which you can think of the air as a fluid, right? So because it's pressing on the air, you're going to get these areas of sort of compression, and then these areas in between where there's less molecules in that space. And if that happens over an even period, you can plot that on a graph, and you end up with what we have down here. So that's a sine wave. It's an even period, meaning the wavelengths, they're going to be even. It's going to pass the same number of peaks and valleys in a second. And the way we measure that frequency in audio is a hertz, the unit of a hertz, which is 1 cycle per second. This number up here in this range that's in the definition up here, 20 hertz, so 20 cycles per second, all the way up to 20,000 hertz. I'm going to be referring to that range a lot because that's the range of human hearing. And those are nice round numbers because we designed this scale for ourselves. But yeah, generally speaking, 20 hertz is sub-bass, super low end, and then 20,000 hertz is so high, a lot of people can't even hear it. So you have low end on the low numbers and high end on the high numbers. Great, yeah, sound wave, nice and smooth. It's the smoothest curve mathematicians have come up with yet. And again, here's some more examples. There are going to be some audio examples in this. So I would recommend if you have some earbuds or headphones nearby, or can just plug into any kind of external speaker or a Bluetooth speaker, I would say try to go ahead and do that. Really anything but your laptop speaker or your iPad speaker would do well. But if not, that's okay. You'll still get the idea of what's happening. In the upper left on this graphic here, we have a high frequency. So basically per time or per second, you're going to have a lot of waves occurring. And then on the upper right, we have a low frequency. So it's going to be less waves traveling through per time. On the bottom left, this is a given frequency. And on the bottom right, this is the same frequency, but at a higher amplitude. So the peaks are higher and the valleys are lower there. So there you go. Nice basic sine wave, okay? I'll give you an example here of a sine wave in a second, but Yeah, you can see on the top here, it's nice and smooth, but then I have plotted out these other typical sources of sound. And so this is part of the reason we can recognize the sound of, say, a guitar from a piano or a flute, is because they actually have these features in here, right? You can see how the guitar is really jagged, piano's a little smoother, but they have these characteristics of the waveform that make them distinct. So with that, I think I'm going to go ahead and switch over to the interwebs here and play a example. So yeah, this first one here is going to be good old, this is going to be 440 hertz. This is good old concert A. And that's it, you know. One thing to point out about this, yeah, 440 hertz. So with these frequencies, frequency and pitch, musical pitch are related. Frequency is sort of a finer gradation of that. So incidentally, 440 is concert A. If you double any given frequency, you end up with an octave higher than that note. So you would end up with an A higher than concert A if you went to 880. And every time you double, it goes like that. Here we'll get 440 again, just to kind of, right? So 440 is down there in what I would call the low mids, right? You know, when we go 20 to 20K, 440 is down there in the low mids. And then we have this one. This is actually the TV test tone. I imagine everybody's heard this at some point. This is 1K. And so because those numbers are, you know, exponential, it happens that 1K is actually in the middle of this frequency spectrum we're talking about. You know, the integers from 20 to say 500 cover a lot more ground on the audio spectrum than say 2,000 hertz to 5,000 hertz. So it gets finer and finer gradation as you move up that scale. And to sort of indicate that, what I have here, this is called a sine wave sweep. So it's actually going to start on the low end at 20 hertz and go all the way up to 20K. So you can sort of test your hearing at the end here. You may not hear anything for the first second or two, and that's, you know, smaller speakers just won't even reproduce those low frequencies. Down between anywhere below about 80 hertz or even below 100 in some cases, they just won't reproduce that sound. And even in a live music environment or other playback environment, a lot of times for us, those frequencies down at the lower end are more felt really than heard, especially if you're at a live music event. You might not actually perceive, say, 30 or 40 or 50 hertz in your ear, but you'll just sort of feel it in the environment. So anyway, here we go with a sine wave sweep. So yeah, I broke my own rule. I wasn't listening with headphones, but you know, I don't think these things are going any more than here. We're gonna do it again. I don't think what I'm hearing is any more. I don't think you're hearing anything past 16K on this laptop. So yeah, that's a sine wave. It's pretty boring, right? And there's nothing to it. But what's really happening typically is we're getting a lot of different sound waves that are interacting with each other, and they're actually blending to form sort of one ultimate sound wave. In this graphic, what we have here is we have two red waves that are not the same, and they combine to form the blue wave. So you'll notice where they overlap, you know, we have more intensity there. And then where the blue line actually moves closer to zero because they're sort of canceling each other out. And this more represents what's going on, you know, in the real world all the time. You know, we're hearing lots of different stuff bounce around at the same time, and especially in music, which is designed to have sound waves that are synergizing with each other in time and all that stuff in harmony.
Hey, Kevin.
Yeah.
Yeah, we have a question from Carla. She's asking,
Mhm.
could you repeat the information about the octaves? You had mentioned earlier that they were simply,
Mhm.
yeah, go ahead.
Sure. Yeah. Let's see, I don't know if I have a great. So later on, we'll see a scale, but just on the frequency spectrum that we're talking about, that goes from 20 hertz to 20,000 hertz. Not every frequency has a pitch associated with it, but any frequency, whatever that pitch, musical pitch is, any given frequency, if you double it, that doubling is an octave up from that pitch. And if you have it, that's an octave lower than that pitch. And that works for any frequency.
Thanks, Carla.
So yeah, so here we go. We're combining a bunch of sound waves, and then I feel the need to throw out this concept that's kind of advanced, and then we're just going to forget about it. But basically, I do like to throw out that it's not necessarily multiple waves. So there's a concept called phasing, where basically phasing can happen with one sound wave. So let's say I have a microphone on a source on stage, and then for some reason, 10 feet away, there's a microphone that's also picking up that source. Okay. So, and it's the only thing creating sound at that time. So these two microphones will pick up basically the same wave, but they won't be time aligned. And so that wave can cancel itself out when it combines either in the soundboard or out from the loudspeakers. So it's just something to be aware of, that time alignment also has to do with these interactions that we're having with sound waves. And in the bottom example, so on the top example, this is halfway out of phase or 90 degrees out of phase. On the bottom example, this is completely out of phase, 180 degrees. If you were to do this in a vacuum or in a piece of software with no other noise involved, these two waves would cancel themselves out completely, and you'd have silence. So phasing, something to know about. Time alignment. Okay, good. And you can forget about that. That's too complicated. What I do want to do though is, so we just heard some examples of sine waves. That's one wave at a time, all by itself, and it's pretty much featureless. It's just this up and down. Now we're going to go to the complete other end of the spectrum, and we're going to listen to some pink noise. So pink noise is going to be all of the frequencies happening at the same time. So we've all heard something like this before. People oftentimes will refer to white noise. White noise is very similar. If this were white noise, this intensity graph here would be all the way flat across the board. But what happens is that doesn't actually sound right to us. And I'll show you why here in a second. So pink noise basically compensates for that by giving a boost to these lower frequencies, and then it scales down as it gets into these higher frequencies. Generally speaking, that's because humans hear higher frequencies a little better, at least in this range, okay? So yeah, good old pink noise. We've all heard this. You know, you used to be on an old TV, you would say that was the snow, but I don't know if any young people have even ever seen a TV do that. With one little side note about this kind of noise, when you get into sound design, especially for theater or sound effects, or for video or TV or film, this sound, there's a lot of plays that call for a sound effect. It needs the ocean waves, or it needs wind, or it needs rain, or it needs applause, like a big audience applauding, and there's a bunch of other ones, and they all sound like this. You could get, by the time you go down to the beach with a fancy microphone and record it, right? And then, that person's going to do whatever processing they do, and they're going to bounce it down to maybe a wave or an MP3. And then by the time you get it and send it out of a loudspeaker for 300-400 people, there's your applause. And the director's going to say it sounds like wind when it's water, and it's this whole thing. But that's pink noise. It's all these things happening at once, and it's boosted in the low end, and I'm going to show you why. This is the reason why. So on this graph, the yellow lines here represent the intensity. So on the vertical axis, the intensity that it requires for us to perceive these frequencies on the horizontal axis, to perceive these at the same level, okay? So this gap right here, you see this space at the bottom left? That's why you need a subwoofer right there, because we don't hear low end so good. Yeah, and then, between about 200 and 2K, pretty flat, pretty normal. And then there's sort of a little uptick, or actually a downtick down here, close to 4K, and then it kind of swings up here. So there's some funny business going on with our own hearing in this region. So this is called an equal loudness curve, and I'll show you a whole other way to look at it. This is the human ear frequency response. So this is the same basic graph, but it's inverted now. This is our response to these frequencies, okay? So again, down here on the low end, below 200, we start to trail off. We don't hear that so good. Pretty flat up in here, and then we start right around 4K, 3K. We have this sort of increase in our hearing sensitivity, and it goes down by 8K, and then we have another one back up around, what, 12, 13K? And it trails off really quickly after that. I'm not an anthropologist, but I have to presume that this is a function of, evolution and basically our efforts to understand human speech, right? And interestingly, this 8K down here where there's a dip, 8K is where the S sounds live. So if I just, handed you a mic and you just went, and we plot that on a spectrograph, it's going to be a bunch of energy right at 8K right in here. That's kind of interesting. Great. So we have sort of a sense of what the waves are doing in the air. And then, so what happens when it gets to us? Your earlobe is basically going to bounce it down your ear canal. The first thing that's going to happen, it's going to hit the eardrum, which is attached to these tiny bones that will vibrate along with it. And then basically you got these canals that are a highway to the cochlea, okay? In the cochlea, there's these teeny tiny hairs that are all tuned to certain frequencies, and they vibrate when they hear the frequency that they're grown to resonate with. And then they're connected directly to the auditory nerve, okay? So here's the cochlea broken out again, and you can actually see the region where these frequencies are picked up in that little spiral. And then it sends that data right here into the brain, where it's then interpreted as sound, or as I like to think of it, the Bluetooth speaker in your brain. People talk about the mind's eye a lot. We don't think about the mind's ear very much. And that is part of the reason I'm kind of starting with on such a basic level, because sound is a little bit harder to conceptualize, if only because we can't generally see it, right? But I'm going to fix that also here in a second. This is another one just to kind of give a broader view of the audio spectrum. So everything we've been talking about is right here on the spectrum, okay? But you'll notice, you got animal hearing that can live higher than that, ultrasounds, other medical applications. And then, and then we also have infrasound, right? So like, maybe we'd know an earthquake was coming if we could hear down here. I like to relate this back to the electromagnetic spectrum. If you look at the electromagnetic spectrum, visible light is like a tiny band. We don't see ionizing radiation, for example. We don't see infrared. So we're blind and deaf is what I'm trying to tell you. And if that doesn't bring it home, I went ahead and threw in some typical hearing ranges for animals. So everybody knows, the dog can hear pretty high. We already knew that. So they get up to 45 kilohertz. But they, we got more low end than them, so maybe they don't appreciate dubstep as much. The bat starts at 2K, so they don't even need a bass guitar at all, but they go up to 110, which is nuts. So that's, that's getting up into here, like into ultrasound territory. I like this one. I didn't know this. The chicken only hears 125 to 200, 2000. So that's not a lot at all. And it made me wonder, is that why they always have that funny face? They're always looking around like they're nervous. It's because they can't hear anything. This one bummed me out. The cow, man, the cow's crushing it. Look, cow even hears better than us. But then this is also interesting to me. So the landline phone, it only transmits audio between 300 hertz and 3400 hertz. That's all you need to perfectly understand human speech right there. And the phone companies do that, I believe, as a reason of just sheer bandwidth, the data of the bandwidth data that they have to transmit. So yeah, and it's funny to me because I don't know if this is still true, but when mobile phones were first becoming popular, it was well known that a landline sounded much, much better than a cell phone. So that's we kind of sped through a lot of that stuff, and that's a lot to take in. I kind of want to go back to some videos here and kind of give you some examples of sound waves kind of working with the environment. This is a resonance plate we're going to see. And basically, they've got it attached to an oscilloscope that can make it vibrate at specific frequencies. So we're going to hear the tone and know that the plate is vibrating at that same frequency. And they're going to put sand on it so that you can see, you know, the effect that it's having on that medium. So I'm going to jump ahead a little bit. So you might notice that as this frequency is increasing, it looks like the patterns are getting more detailed. Well, that makes sense because these wavelengths are getting shorter and shorter as we go up in pitch. So that thing's pretty cool. And we're going to have links to all these videos in the chat at the end of this. But then there's also, anybody ever heard of a Rubens tube? Basically get a tube, you cut a bunch of holes in the top, you have a flammable gas that's pumped into it, and you can put a speaker at one end or sometimes multiple speakers along it, and you can see what the pressure wave is doing in the music. So I think he might have ran out of fuel there towards the end. And then this is a video that kind of illustrates some of these same concepts, but just in a little bit, more musical presentation. I'm not going to play this whole thing. So yeah, and then, that video we just watched is I think the point of that video obviously is sort of the visuals, and that's cool, but it's just showing you what audio is already doing around you, whether you notice it or see it or not. So the visuals are cool, but it's not the visuals that make the audio cool. The audio is cool all by itself. So yeah, we've been talking a lot about frequency. Let's talk about intensity. In audio, we measure sound in decibels. So that's a log 10 scale. And the reason that we need a log 10 scale is because the variance in intensity is just so astronomical. We needed something to make it more easy to work with. But there's a big distinction here. So on the left side, we're talking about decibels in terms of sound pressure level. So that's the loudness that you would actually experience in a room that's having audio. And there's a graphic there that just kind of shows some typical intensities in decibels in sound pressure level for some common sources. Okay, so that's pretty simple. Normal conversation at 60 dB down there, a lawnmower at 90, and so on. anything, I think, what is it? I think anything more than 90 for like a half hour is where you're starting to get into hearing damage, permanent hearing damage. But then there's another place that we use the decibel measurement, and you'll see that on sort of components like a mixing board or other components of audio gear. So if you look here on the right, you might see a meter like that on a soundboard or something. And it's funny to me because notice it doesn't even say like dB what, like decibels relative to what. So, back in the day, you would see like dBV for volts or, less than a volt, and then dBm for a milliwatt. It's a decibel relative to that. So the big takeaway for me on this, especially for new engineers, is what you need to just know is that if you have a fader right here at 0 on a soundboard, and then you push that fader up to 5, yeah, you increased it 5 dB here relative to the power that that signal has, but you didn't necessarily raise it 5 dB out into the sound pressure level, the actually intensity that the audience is experiencing, for example. It could actually be more than that if you raise it that much. It could be a bigger difference. It could be less, depending on your gain structure. So we have decibels relative to loudness, which we call sound pressure level, and then we have decibels relative to the signal strength of the audio that's in our sound components that we're working with. And I do, there's a lot of words on here, but I do like this one. So yeah, in terms of power, a jet engine is about 1 trillion times more powerful than the smallest audible sound. So hence log 10 decibels. And then another concept to be aware of with sound is the inverse square law. And basically just what it's saying is that as you move away from the source of a sound, the intensity of that sound is going to drop exponentially. I like this graphic on the right. I mean, it makes perfect sense. If there's a singer on stage, Pavarotti is right here and I'm standing here, he's going to be loud to me. I'm getting a lot of the energy directly from him. It's all hitting me. If I go to the back of the room, well, that's all spread out now in these vectors. And so I'm not getting as much of a chunk of, the energy that they're producing. So inverse square law. And where we think about that a lot is microphone placement. Sound guys are always telling you to get the mic closer. And you think about that with speaker placement and how you're going to cover your audience and stuff like that. So that kind of ends the sound wave portion. Microphones. So microphones are one of the main ways that we capture audio and get it into a mixing board or other components that we're going to use to either make it louder or change the quality of it or mix it with other sources. So yeah, I just put a little collage together here, whole bunch of different types of microphone. We've seen handhelds a lot. There's some shotgun mics right here. We've got a large diaphragm condenser microphone. We'll talk about what that is. Some lavaliers, some body mics down here. And then this guy, the SM58, you might not be able to read it, but it's right there, legendary vocal microphone. Yeah, I agree. This is the workhorse of the music biz, I would say, the live audio biz. They're everywhere. They're only about $100. They're super durable, and you can mic almost anything with them and get a pretty okay result. I would venture to say that 30 to 50% of every microphone that the average person has ever seen is an SM58. So it's like the Toyota Corolla of microphones. Two basic types of microphone, the principles of when they work. And there's others, but these are two of the primary ones. So dynamic mic, condenser mic. So the dynamic mic on the left here, the way it works basically off of a pure resonance concept. So if you look at this graphic, there's a really thin diaphragm on the front of the microphone right here. And that's usually made of a really thin, like a paper fiber. And what it's going to do is just resonate with the sound that's coming into it. It's attached to a wire coil that goes around a magnet. So when this little guy vibrates just a little bit, it's going to produce a teeny tiny electrical signal that is a mirror image of what the diaphragm picked up, what it resonated with. And when we send that on down the cable to the mixing board, and we'll talk a little bit about that process in a minute too. So that's pretty simple. You got a coil and a magnet. You got something that's going to vibrate attached to it. SM58 is a dynamic microphone. Most of the handheld microphones you see, like a singer is holding the mic up to them in their hand, most of those are going to be dynamic microphones. But then the other primary type would be a condenser. And so the condenser works on a little bit different principle. It's going to require a power source, not a lot, just a little teeny tiny current And usually that'll actually be, it'll be powered from another component through its own mic cable. So a mixing board can usually provide the power. It's called phantom power in that case, or you can just have a little battery box that'll send it the power that it needs. But what that charge does is it effectively floats a plate off of a back plate. So this guy in the front is just kind of hovering now. And that, what that does is it makes it way more free to vibrate and resonate with the sound waves that are coming into it. Okay. And because it actually is connected back, it already has an electrical connection. We don't have to worry about the magnet in the coil. It's gonna reference itself to the back plate. It's gonna create that charge in between them as it wiggles, and then it's gonna send that down the cable. The two easy things and important things to remember about condenser mics is they need some kind of power source, and they're more sensitive than dynamic mics. And that's not a good or a bad thing, just depends on the application. You might not want to give a condenser mic to a metal vocalist, you know, but if you're miking a symphony, like with choral mics from a distance, that's a great application for a condenser mic. If I go back a slide, like I said, the SM58 is going to be dynamic. These shotgun mics, they're going to be condensers. There's a large diaphragm condenser. You see these a lot on radio. It makes people, you know, they're not singing. It's not like they're singing loudly. They're just talking and they want to sound like, you know, the NPR guys. So there's a large diaphragm condenser. This guy looks like probably a kick drum mic. So that's probably going to be a dynamic mic. There's a tom mic. So yeah. And all of the lavaliers, by the way, all of these are going to be condensers. So there, dynamics and condensers. Another property of microphones is going to be the polar pattern or the pickup pattern. So in this image, the front of the microphone is going to be the left side. So three very typical polar patterns are going to be the cardioid. So it kind of like listens all around it and not so much from the back. You have a hypercardioid, which is a little bit more focused. It's a little bit more oblong up front. So it's going to kind of reach out towards the front a little bit more. It rejects off axis back here. And then I actually don't know the reason for this, but it does pick up a little bit from the rear. And then you have an omnidirectional microphone, which kind of listens all around it. Here's another way of looking at that. So this would be the cardioid. And so yeah, cardioid, kind of heart shape, looks like an upside down heart. And so I'm not going to pop out my camera, but I've got one here, okay? And so what this is showing you is that it's going to listen like this and up front, but not so much from the rear. And you know, that sort of makes sense because the body of the microphone is in the way, right? So that's a cardioid, very, very typical, common polar pattern. And actually, a lot of times, well, you can't really see that well, but a lot of times it's going to be that shape will be right on the microphone itself somewhere along the rim to indicate that's the polar pattern. But then you have super and hypercardioid. They're basically the same. They're essentially the same thing. So supercardioid, a little bit narrower, so it listens a little bit less from the side and a little bit more up front. And then it rejects from 30 degrees off axis in the back, and then it does have a little pickup from the back. So you can kind of see cardioid's a little fatter, right? The hypercardioid's a little more focused up front. Again, this is just stuff to be aware of as a property of a microphone. I don't think about this every day if I'm going to set up a band or whatever, but I'll tell you an example of a time to think about it is, let's say I'm getting feedback, microphone feedback. So that's when basically the microphone can hear its own output from a speaker source nearby. So, you know, if a vocalist on stage will oftentimes have a monitor speaker that's pointed back at them and feeds them some of their self and what else they need to hear from the band on stage. If I'm having a feedback problem and I'm using a mic like this, well, maybe what I want to do then is take their monitor and move it off axis over here where it's shooting into the dead spot of the microphone to help sort of mitigate that feedback a little bit. If it's a cardioid microphone, maybe I want to put the monitor right behind it, right, to try to minimize feedback. Of course, the problem with that is as soon as, you know, if I do that, as soon as the vocalist takes the microphone and goes like this or that, we just change that whole relationship. So, but anyway, that is a time that I might think about the polar pattern. Otherwise, it's just something to be aware of. I don't sweat it when I'm grabbing microphones for an event. Okay, so just like our ears, we're kind of going back to frequencies now. Just like our ears, these microphones will have a characteristic frequency response. It's what they're good at, you know, what they're able to reproduce and send down the cable. So Good old SM58. Like I said, this is a $100 microphone. And look, it looks a lot like our hearing actually, right? After about 100, not a lot there. So not a good microphone for a bass guitar or a kick drum, although I have done it in a pinch. And yeah, and then there's some funny business. I presume this is just a sort of I don't know if this is a design feature or just a character, it's the physical limitations of the microphone. But yeah, again, this is a $100 microphone and it works great for most applications. Now down here, so the Crown PCC, that's a floor microphone. It's used a lot for theater to pick up sort of the whole stage. It's used a lot for tap dance and stuff like that. It can also be used just as sort of like a board meeting. You just set them out on tables. But yeah, you'll notice the line that's not dotted here is pretty flat, even below 100. It still has some low end pickup, very flat through here. And then it has like a kind of a little funny business, but not too much. What we say about 5K and above, not too much. So this is a $300 microphone. And then one of my favorites, the Shure KSM32. So that's the same manufacturer as the SM58. This is a large diaphragm condenser. And look at that frequency response. I mean, almost all the way down to 20. And then, a little wiggle up in here. And my face is in the way, but I think it's pretty good up in here too. That's a $400 microphone. And for those of you keeping score, this is the microphone we use to record the actors for Argo, by the way. So yeah, $100 microphone gets you this, $400 microphone gets you that. And I got to say, this one sounds a lot better. You can do great things with an SM58. A good engineer can apply some subtle EQ and stuff like that and get it a workable, product. But KSM32, sometimes you get what you pay for, I guess is what I'm trying to say. What are these other lines here? So on the KSM32, there's a switch, there's a selector on the microphone itself, which will actually cut the low frequencies if that's what you want to do. When I'm the engineer, I don't usually do that because I would rather just get all the information from the mic and I can deal with it at the console. But there might be a reason you wanted to do this if you weren't, if you had limited mixing ability or something like that, if it was going straight to a recorder maybe. The Crown PCC actually has a boost in it, so it can actually like increase the sensitivity of its low end pickup. And this is probably an okay time to go ahead and touch on EQ, equalization. I don't really have EQ in the scope of this presentation, but I will say, anybody, if you've ever played with the bass or treble on a stereo, that's EQ. We started off by saying 20 is on the low end and 20K is on the high end. I mean, that's what EQ is. And so, yeah, there may be a case where you wanted to boost a low end pickup from that mic to make it sound a little beefier, or there may be a case where you wanted to cut it before it even gets to the soundboard because you're getting a lot of low end from a source. And again, I don't really have an EQ slide, but since we're talking so much about frequencies, I will say one of the things I tell new engineers, one of the biggest problems with giving somebody a microphone who's going to speak is that for various reasons, the microphone can sound a little muffled to the audience. And there's just a million things. It could be where they're sitting. It could be the loudspeaker placement. It could be how they're handling the microphone. They could just have a really deep voice even. All kinds of stuff can happen to make, reinforced speech less intelligible. And if you don't remember anything about frequencies today, I would say if you're miking somebody and they're giving a speech, say, and they're hard to understand, one of the first things I would do is I would go to the range about 200 and 250, which is the low mids, and I would cut that out. I would do like I would scoop it out, something like this, maybe 3 to 6 decibels. And the reason for that is that low end, that low mids, that doesn't help your intelligibility really whatsoever. It's just sort of, it makes you sound, sort of manly if you're, if that's what you want, but it doesn't help you understand speech. So I usually cut that out. Somebody that has too much low end in their voice, it's going to sound kind of like this, or, how a lot of people do with their mask on. The other thing, if I do that and I'm still not satisfied with the intelligibility, the other thing is I'll come up here into the sort of upper mids or, well into the mid range, or somewhere between maybe 2K, 2000 hertz and 5000 hertz. And I'll actually boost up in there. The reason for that is that's where a lot of your consonant sounds lives, like your S's, your T's, your F's. And these are the things that make speech intelligible. So again, there's just a little mini crash course on EQ. And maybe at the end we can get into some more of that EQ stuff. But anyway, mics themselves have their own frequency response. So that's something you got to keep in mind when you're miking something up. And then this is just to sort of pull things together. I haven't really talked a lot about the mixing and processing side, but just the point of this slide really is that the microphone on the input side and the speaker on the output side, the loudspeaker, they're working on the same principles, right? You got a coil and a magnet. This one's going to wiggle teeny tiny. We're going to send it to the sound booth, hopefully, get it sounding good. We're going to blend it together. We're going to put some, special sauce on it. And then we're going to send it to the amplifier, which is going to kick the power way up of whatever's coming out of the mixer, and ultimately to be able to power a loudspeaker. And so you've taken that waveform from this microphone and maybe some others, you blended them together, maybe you put EQ on it, you got it where you wanted it, you send it out to the amplifier and ultimately the loudspeakers. And they're working on the same principle, coil, magnet, and it's just going to vibrate and make the sound. Now, obviously this is a cross section, so this would go all the way around in a circle, this cone would, or this diaphragm. But one thing I always like to point out, this is the best explanation I've gotten so far for the, at some point I started wondering, so how on earth can this one membrane, this one contiguous piece of material, how could it possibly reproduce, all of these sounds at the same time and actually at different times, So if I play, a recording of an orchestra out of here, it's going to be making all these different sounds at all these different times. And some of these sounds are going to be happening at the same time, right? Well, the way it was explained to me is that what you have is basically the greater part or the outside part of that cone is sort of pumping, right? Sort of pumping the air at a lower frequency. And that's where you're going to get some of your low end from. And that's why larger speakers, by the way, are able to produce better low end. But while it's pumping at that frequency to do, say, the bass notes, other regions in the cone are actually vibrating at all different frequencies necessary to make the sounds at the time that, that it happens in the recording. So to me, that's pretty darn cool that, you can have this one piece of material, one speaker, and literally you could play back, any piece of music and it'll make all the sounds for you. And then, okay, so we got to get into the weeds a little bit here because we got to know what happens after it leaves the microphone and how it's going to actually travel into the cable, through the cable, and get to our soundboard, right? So the big concept here is balanced audio versus unbalanced audio. In the top example, this is unbalanced audio. And so basically you have one wire in that cable that's carrying the electrical signal that is the waveform, okay? If it picks up any noise along that cable path, and by the way, if I'm at Stewart Theater and I plug a microphone into a junction box on stage, I would estimate that there's probably 250 to 300 feet of cable between me and the soundboard and that microphone before I get to even do anything with it or boost it or anything. It's got to go, I'll probably put a 50-foot cable on it so that, it's a comedian, say, so he's going to be able to want to walk around. So he's got a 50-foot cable. It plugs into my junction box, which goes into a conduit, and it's going to run over to the wall, up to the catwalk level, down the catwalk. So this is why this is important, because there's a lot of places for noise to be picked up, and there's a lot of opportunity for that signal to just decay to where it's just not even strong enough to work with. So again, so here we go. Unbalanced audio, we have one wire carrying the signal. If it picks up any noise, it could be from a power source or another component or just electromagnetic interference, anything like that, it'll stay in the signal. So generally speaking, for live audio, we don't like to run unbalanced cable more than really 10 feet. In contrast to that, balanced audio does something different. To transmit balanced audio, you have to have at least two wires that are carrying the signal in addition to the ground, okay? And the way this works is, so we talked about, how far do I have to go back? So what's happening here with these two wires is if the microphone diaphragm is at rest, okay, and it's going to start to vibrate. So it's basically, it's going to go past zero, that's going to be positive, and it's going to bounce back on the other side of zero, and that's going to be negative. You're getting this inverse of the waveform. So positive, negative, okay? Two wires in the ground. So we do our pathing, we run our cable our 300 feet, it picks up the noise, but here's where the magic happens. When it gets back to the soundboard is designed, it knows with this input, it's going to take the inverted signal, it's going to re-invert it, and it's going to sum it with the positive. And what that does is it cancels out all the noise you picked up, and it actually reinforces the original signal. So balanced audio is pretty magical, and it's the reason you can just take a little old microphone and whisper into it and still hear it well at the mixing board, you know, some distance away. In the real world, this kind of looks like this. A couple examples of unbalanced mono cable on the left here. So we have a 1/4 inch and then the 1/8 inch, or what people think of as an aux, 3.5 millimeter. And then here's your balanced over here. So this is XLR cable, mic cable. So it's got 3 pins in it, right? Your positive, your negative, and your ground, you know. Not to be confused, by the way, with 3-pin DMX, which is lighting cable. And in a pinch, if your sound guy will let you, you can use mic cable for DMX, but you should not use DMX for mic cable. It's a thinner gauge. It's not as good quality. So there's 3 big concepts actually on this slide I want to touch on. We talked about balanced versus unbalanced. There's also the concept of mono versus stereo. So in this case, so I have a 1/4 inch cable example right here. And if you look closely, there's a divider right here on this plug. And so basically that's your signal is going to contact here and your ground's going to contact here. Okay. So that's just called tip sleeve sometimes, TS 1/4 inch. If you look down here, there's 2 bands that are dividing this plug. So actually I have 3 sections, okay? Now you might think based on what I just told you, okay, so that could be positive, negative, and ground. But generally speaking, that's not gonna be the case. These cables are usually used to transmit a stereo signal. So that's gonna be a left and a right separately, versus if you plug this into a stereo output with just the one divider, you're either only going to get the left side or you're going to get both sides combined together, summed together down that cable. Since we're on the topic, a DI box, a direct input box, the only thing you need to know about these is they convert a unbalanced signal into a balanced signal. Say I have somebody with an electronic keyboard on stage, there's no microphone involved. It's just going to output audio directly. I don't even have a microphone, but it is going to be generally sending out unbalanced audio. So what I'll do is I'll take a 6 or 10 foot cable. I'll take it out of an unbalanced output that might look like this. Okay. I'll plug it into a DI box, and now I can use my mic cable and I have a balanced audio signal the rest of the way. And now I can run it long distance back to the soundboard. Nothing to get hung up about there. DI box makes an unbalanced signal balanced. And the fact of the matter is most modern soundboards, they will only take a balanced input anyway. So sooner or later, you got to convert it over to an XLR. But yeah, you might see this on the back of some things. Notice, so you got your XLR out, and then you got your unbalanced out. 1/4 inch, generally 1/4 inch is going to be unbalanced, and generally XLR is going to be balanced mono. Okay. And then the other concept, I think I see it here. I see low Z, which stands for low impedance. I see this right here. This says instrument or line level in, and then mic level out. We don't have to worry about this too much these days because a lot of equipment will just impedance match for you. Basically, instrument or line level is going to be quite a bit stronger of a signal than mic level. And that's the only thing you really need to know about that. And then just to sort of scramble your brains a little bit, I know there's a lot on this slide, or a lot of stuff I'm talking about here. If you get out in the world and you're trying to do any of this stuff, just know that if somebody hands you an adapter cable that has an XLR plug on one end and say a 1/4 inch on the other, okay, that's an adapter, and it'll make it fit into whatever you're trying to do if that's what you need. But it's not going to be balanced, right? So just because I remove this plug and solder on an XLR to make it fit into my soundboard, that didn't make it balanced. You got to convert it to balanced, usually with a DI box. This will just break it out a little bit further. So in an unbalanced cable, I just have this one wire that's carrying the signal, and then I have a ground, which also actually doubles as the shielding. What they do here is they braid it around the core, and it acts as the ground, but it also helps try to resist interference. Okay. And then here's the inside of a balanced, like a mic cable. So you get your positive, negative, your ground, which is also your shielding. And there's usually a little bit of like stuff to toughen up the cord a little bit in here. One other big distinction is, so this here, these on the bottom are pictures of speaker cables. So this is still a 1/4 inch plug, right? But it's not a signal cable like we were looking at over here. These are, I can tell just by looking at them because this is molded and that's really thin cable. I can tell by looking at it, that's a signal cable, okay? This is a speaker cable. The difference is it's not going to be shielded. It doesn't need it because it's already passed through the amplifier. The signal's so strong, it's not it's resistant to interference after it leaves the amplifier. So it's not shielded, and it's maybe hard to see in this picture, but the gauging of the wire is quite a bit thicker because it's carrying more power. So yeah, just because you see this plug doesn't necessarily mean that it's a signal cable. Signal is a much thinner gauge than a speaker cable. In a pinch, you can use a short speaker cable for a signal cable, but I would recommend against using a signal cable for a speaker cable because it's just too thin, and it could melt on you. And yeah, so that's how we get the sound from the mics to the soundboard, and that's kind of usually where I like leave it off for this portion. Just a little schematic here to kind of like try to tie this together. So yeah, you got a mic input on stage. Maybe it goes to a junction box that has a lot of inputs and outputs on it. Okay, it's going to feed my channel inputs to the soundboard. I'm going to turn some things up, turn some things down, do what I got to do, and then and it may even route outward over here. It may even route out to some other components. You know, I may run somebody's microphone through a fancy preamp or a reverb unit or something. So it would go out of the board and then back in. Ultimately, it all blends together and we send it back out to our amp system. And that's what's going to feed the speakers, what everybody hears.
Well, Kevin, Carla, good to know what causes feedback. What was your biggest challenge when doing sound for Brightstar?
I guess actually Brightstar was one of the funnest musicals for me to mix. I like mixing in the Titmus. It's really intimate. There's a lot of good sound treatment in there, so it sounds nice. And because it's intimate, I don't have to like blow people away with the audio. If you go to an arena show and you're in the back, I mean, you're not hearing the actual band at all. All you're hearing is the PA. But in a room like the Titmus, I was able to blend the sound that was coming off the stage and just sort of reinforce it and not have to have like rock and roll level audio. So it was fun. It was fun, and the band was really good. It sounded good. It was a lot of instruments. It was a lot of instruments really tightly configured. So I had a ton of microphones close together, and I had a lot of things that sounded the same. So like I had I want to say I had 2 violas and a violin, something like that. And when in the middle of a show, sometimes it's like without throwing on the headphones and trying to solo out individual channels, it's sometimes like, wait, I need more viola, but I'm not sure which one, you know. Yeah, no, Brightstar was probably one of the least challenging. Things kind of came together, but it was a pretty big band for a pretty small area, and I had just a bunch of microphones all jam packed together. Yeah, I'd say that.
Yeah, Carla, I would also say, like, I would agree with that. We on most of our musicals in which we have the band on stage and sometimes in the pit, in Stewart, space is always our biggest concern because we have Kevin, who needs to get his equipment in there, the musicians who want the space and need the space to move about. And for those shows in which we have the production and the band together on stage, the director and the actors and the scene designer, they need space to act. So we've got a lot of people vying for the same real estate. And every time we come to an agreement, but it usually is a little,
Just up it by 30%. Right. I'm telling you, just go up 30% on the space every time.
Well, Michael Davis asks, what do you go through on a sound check before a concert?
Yeah, so if I have a band coming in, let's say we think the band's going to arrive, say at 1 o'clock, and then we're gonna do a sound check at 2 or 3, maybe something like that. I'll have this is key. You're not really a band if you don't have a stage plot and an input list. So somewhere in a professional band, in their contract writer, they'll generally provide you with an input list, what the inputs are and what the microphones they prefer, and then a stage plot that kind of shows where it goes. And what I do is I try to set it up to as closely as I can to what those documents ask for. And I'll literally, for most instruments, I'll just kind of go through and as far as checking, I'll just make sure that I have a signal. I mean, oftentimes I'll just have a stagehand just kind of walk in front of every microphone and just kind of snap their fingers, and I'll just make sure that I'm hearing it at the board. So I know that signal path is good. There are going to be some cases where you can't really do a check because it's, say, like in the example of a keyboard. I have somebody who's bringing their own keyboard. Well, I can't actually check that, but I could plug something in, and generate a little noise and make sure that the cabling is working and it's showing up where I think it should on the soundboard. So as far as checking, that's the basic one. One little thing I learned over time is that let's say you're setting up a PA from scratch, like you're doing a festival concert and you're going out to a field and you're setting up a PA. For me, I found that it's always good practice to get your speaker systems up and tested before anything else, because you can get really slowed down and bogged down by getting all your inputs, set up 20 or 30 mics on stage and run them this way and that way. But if you do all that and then you go to check your PA and it's not working, like you have a big problem. So I always got in the habit of, I want to check my speaker outputs before I even plug in a microphone, generally speaking. And then so I've checked the speakers obviously first, and then we've plugged all the mics in and what are our inputs, and we sort of line checked all those. And if I have time, I'll go in and sort of do a very, very basic, like extremely basic EQ on the channels. All right, so for example, for vocal mics, I'll probably chop off the low end right away because I don't think I need it. I can always put it back in later. If it's a bass guitar or kick drum, I probably won't do that. I'll let the low end fly until I hear what it sounds like. And then we didn't talk about compression today, but basically compression is a way of sort of automatically leveling things a little bit. And I'll usually go ahead and throw a light compression on every channel just to help me funnel things, into the blend. And then once we get into a sound check, I can kind of scan across on the meters and see if I'm compressing this too much or whatever. And then if there's still time, I'll put a little extra focus on the vocal mics, because that's usually vocal mics are kind of your biggest, workload with a band. They're going to need to hear themselves back. So I'll try to maybe rough in their monitor mix a little bit where they have their vocals in it already. And if I get that far, I'm doing great.
Well, thank you all so much for joining us today on How to Theater Audio 101 with Kevin Wright. So again, thanks, Kevin. Thank you. And we'll see you around.
Yep. Thanks, everybody.